Hello, and today we're going to talk about the second to last installment for Unit 9. This is going to be on seismic waves and how we use those to study the Earth's interior, sort of give the Earth a sonogram. Seismic waves travel throughout the entire Earth, although we will talk about some shadow zones, but we're talking about the body waves, S and P waves. P waves where the action of the wave is in the same direction that the wave moves, and the S wave where the action is perpendicular, so it moves a little slower, 6 kilometers to 4 kilometers per second, respectively. These are both body waves, and they're picked up by seismometers, seismographs, and they're written down on a seismogram. And then scientists can read read information about earthquakes that happen everywhere on the planet. Seismic waves are X-rays that look inside the Earth. P waves travel through because there actually are size changers. Solids do not like their size change, so it'll pass through a solid. Liquids do not like their size change, so it'll pass through a liquid. Gases can be compressed and expanded, so it will not pass through a gas, but that works out really well because the Earth doesn't have gases inside. Picture you see here is actually talking about an Earth that is the same all the way through. Um, so basically what scientists used to think and what people used to think was the Earth was the same material all the way through, and if that were true, seismic waves would go out of the focus located below the Earth's surface, right below the epicenter. They would go out and they would actually turn toward the surface. So you can see all the ones on this side are turning that way, all the ones on this side are turning this way. They're actually turning surface side, and that's because as the material gets denser on the inside, it moves faster. So this side moves faster, this side moves slower, and because of that it actually turns this direction. But if you had a homogeneous Earth, same material all the way through, these are exactly the way the waves would act. You'd see these waves all the way around the planet. S waves are shape changers. Solids do not like their shapes changed. Liquids don't care, and gases don't care. So because of that, S waves only travel through solids. And if you take a look at this diagram, we still have this earthquake going off, still coming out of the focus directly below the epicenter, and again turning toward the outside, the crust, but you actually see that there's a shadow zone, and this S shadow zone, meaning the S waves do not make it down to this point, actually say that the Earth has a low velocity core, liquid. So the outer core actually blocks the S waves from making it any farther than that point. That's going to be 104 degrees away from the earthquake, so down a little bit lower, but in the same location. Here's the actual picture of it, 105 degrees, sorry. And you can see P waves black, S waves red coming out of the epicenter. They don't really come out of the epicenter, they come out of the focus. But you can see them turning toward the crust, and you can see red and black, red and black, red and black, and then that's the last red one you see. Then we get what's called the P shadow zone because as they're actually bending this way, they bend toward the crust, or they bend toward the outside, and they bend this direction, and then they move into something that is not quite as dense. So they move out again, and they bend toward it. So we have a shadow zone where nobody in this location actually gets to see that earthquake. So we get a P or an S shadow zone, a P shadow zone. S shadow zone is this 105 to this 105. P shadow zone is 105 down to 140 on both sides, and then we get P waves that actually made it all the way through the core, both the liquid and the solid. And you can see they're still changing. The only ones that go straight through are the one that would actually land right there, and that would go straight through the Earth and pop out the other side. But we have no S waves between 105 degrees both directions, no P waves between 105 and 147. Remember, P waves come first, and then basically we have nothing there, and then just P waves in this location. S waves only travel through solids. Looking at it again, we actually have a relatively complicated view, but we come down to 105 degrees, then we get a P shadow zone, S shadow zone the whole way, and then P waves down here at the bottom between 140 and 140. Seismic waves travel faster through denser materials. Because of this, the path traveled by the seismic wave bends towards the surface, like a tank. Here's a picture actually showing a very complicated, even shows you the S waves, the pink waves actually moving in that zigzag S pattern, and the blue P waves actually traveling in a straight line. People located right there's the focus of the earthquake. People here get to see both pink and blue. Pink and blue. Over here you get very, very weak P waves, and then you get P waves down here, and again weak P waves. So the S shadow zone from that point all the way around this point clockwise, and then the P shadow zone from 140 to 105 in both directions. I'm going to see if this works. I want to show you a program. Actually, let me show you the program the right way. If I open up Chrome here, should have done this before. And if I open up Recent, if you Google Alan Jones and then seismic waves, you'll come to this program, and there's an excellent program called Seismic Eruption. Hit the EXE, and then down a little lower, seismic waves way down here at the bottom, EXE again. And then if you do that, you can hopefully, is this going to open up? Looks like it's not going to open up as designed. It's got to be in here somewhere. Seismic. Actually, let me do it this way. Setup. Did you see a... Okay, I'm not doing it that way. Sorry, this is taking longer. Let me go back to, and this is Windows 8, seismic waves. Click Start, and you can click actually lots of different pictures. I'm going to click the North Ridge, and what we're going to do is we're going to see there's the earthquake. Happened right there. Here come P waves and S waves. Again, they're moving toward, they're going to hit, and some of them are going to bounce back. They're going to come down. Notice we're only red. Going to hit that. Some of them will come back. Notice it breaks off, so we lose the P waves in this location. And then here comes some P waves. And you can see it's very complicated. I'm glad somebody else, and you can see them up here. P waves first, then S waves, and then we get the surface waves showing up. And it'll keep doing that, but I'm going to lose interest. Another program I'd like to show you. I'll go ahead. Sorry about that. Another program I'd like to show you is Seismic Eruption. Beautiful music. Click Start. Click Go. And you can actually pick a couple of different things, but what I'm going to do is I'm going to pick North American group. I'm going to go up to the Alaska group. And if we actually see Cook Island, these are earthquakes happening in between Cook Island and Alaska. And if you look at the colors, and it looks like we just had a volcano go off. That's the banging. But if you look at the colors, we have dark colors located over here, then reds, then kind of pinks and purples, and then greens, and then blues, and I don't see any yellows. But basically what you've got is you've got an earthquake setup that shows you that it kind of digs down in this direction. It gets deeper as you go this way. And what you can do from this one is you can go back and then pick this, nope, not that one. The top one, do this cross section, and now we have the surface up here, and you can see that the earthquakes are actually telling you that the plate is dying. This plate's being thrust down underneath it, and then it's rubbing it up against this plate, and as you get that, you get these earthquakes. And if you look at the surface, you get the blues all over there, and these kind of turquoise over there, and greens. Looks like we do have a couple yellows, and then the pinks, and then the purples, and then the reds, with a couple of really shallow earthquakes located up there as well. Okay, let's go back into this slide. Seismometer, nothing more simple than a seismometer. It's just a weight hanging on a spring, and you have a confiner on there so it doesn't bounce back and forth. And this weight's got a pen on it, and it's got a revolving drum. And this one's going to be actually for a horizontal type plate motion. This one would be more of a vertical plate motion. But you've got this thing moving and back and forth. Seismometer records vibrations, rotating drum on the paper, usually a red line, could be black and green, lots of different colors on a sheet of paper. As it moves through, the vibrations show up on the paper. However, large masses tend to stay in place, so that mass actually stays there and it goes, and I'll show you one right here. And what you have from Norton and Company is you've got a box that's actually bolted down to bedrock, and what you do is you clear off the sediment, you make this into a hole, you put a canister there to keep soil from crushing coming in and water coming in, and then what you do is you take a drum, put paper on it, take a weight, put a pen on it, hang it from your box, and then you spin it. You can see it's moving a little red line, and here come the seismic waves, and you got P waves and S waves, and then it settles down, and then you can cut this out, and you can actually see we've got P waves, S waves, and surface waves moving through time. Okay, let's minimize those. Measuring earthquakes. There are at least 20 different types of way of doing it. We're going to talk about three: the Mercalli, which I call the three little pig scale, the Richter scale, which I call the magnitude scale, and a moment magnitude scale, which actually talks about all the things, and I lost one there. Magnitude is the measurement of the earthquake strength. It's based on the waves moving through sediments or rock from the fault. Strength. Intensity or strength of an earthquake is measured in two ways. The first way is Richter scale. This measures the amount of energy that the earthquake releases. Each number magnitude is 10 times stronger. So if you've got a 2 and you go down to a 4, and this one's only detected by a seismometer, this is felt by walkers and windows and doors rattle. That 2 to the 4, that 4 is actually 10 times 10, 100 times more powerful. Go down to a 6, and that's 100 times more powerful than that, or 10,000 times more powerful than that. And then this is actually 100 times more powerful than a 6, or a million times more powerful than a 2. So very, very, very strong. Richter scale is a rating of the size of the seismic waves as measured with a particular mechanical seismograph. Developed in the 1930s, they were all over the world, used by geologists 50 years later. We now use electronic ones that don't use the mass, but they work by the same basic idea, and provides a very accurate measurement of even very, 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 very small, much smaller than 2 earthquakes. Does not work for big ones, especially if they're far away. Mercalli's system I call the three little pig scale. It measures the amount of damage caused by it. So if you actually live in straw houses, you're probably going to have more damage due to the earthquake than you would if you had stick. And if you lived in a stick house, more damage than you would if you lived in a brick house. Ranges from Roman numeral 1 to Roman numeral 12. Based on a common earthquake occurrence, such as is it noticed by people? Did it damage anything? Did it damage buildings? Did you have chimneys and roofs fall down? Did you have fissures open up in the ground and swallow things? Again, the Roman numerals, and you can see as you go down this way, goes from almost noticeable to severe damage. Wide cracks appear in the ground and waves actually seen. Developed in the 20th century. Developed in the 20th century to rate earthquakes' intensity. Intensity of the earthquake is actually the motion of the ground in place. It is not a very precise measurement. It does have 12 steps to explain damage by buildings, by what it does to people, and the same earthquake have different Mercalli ratings because of different amounts of damage in different spots. Three Little Pig. And it is done by Roman numerals. Let me show you the shockwave file. Hopefully we'll bring this all into perspective. Okay, if we do a 1, there's the earthquake. Notice we're on pipes in a mine. The car honks, people minding their own business. Go to a 2. Do we notice anything different? Oh, people are noticing it. Woke up somebody or made them open the door and look. Go to a 3. Birds took off. More people are noticing the earthquake. Looks like lights are swinging back and forth. 4. Car moves. Lights are moving. Buildings still look okay. More people notice it. Get to a 5. Looks like doors start swinging open. More people notice it. Get to a 6. And some damage. People start getting knocked down. 7. More damage. 8. Drivers have trouble staying on the road. So the cars are jumping up and down. More buildings. Go to a 9. Okay, looks like the buildings are getting hurt. Go to a 10. Dams are seriously broken. There go the water pipes. And we haven't even gotten to 11 or 12. Bad stuff. Okay. The moment magnitude scale is actually used by geologists today, and it rates the whole earthquake system based on the total amount of energy released by an earthquake. So it's adding the P waves and the S waves and the surface waves to it. It can be used for faraway earthquakes, even if they're relatively small. Some news reporters may actually mention the Richter scale, but the moment magnitude number is probably the one that's being used. If you take a look at this, this is the moment magnitude, and we're talking about kilograms of explosive, and that is a very big number. Millions, billions, and trillions. So 56 trillion kilograms multiplied by 2.2 pounds, that's a much bigger number. If you say in 1960 there was an earthquake in South America, biggest one on record, looks like it was about a 9.6. If you use the Alaskan, a little better than a 9. Krakatoa exploding back in 1883, world's largest nuclear explosion. Mount St. Helens eruption, more earthquakes on this side, more bombs, and a large lightning bolt. And also look down here. If you look at this list, this is a moment magnitude scale again too. We had Virginia going off there. This is the 2003 Virginia earthquake. The 2011-13 August 23rd would have been a 5.8, so it would have been actually about right in about there. You can see San Francisco 89, San Francisco right there, 1906. Chile earthquake in 2010, 8.8, and then you throw in some deaths. 1556, we had 750,000 people die in an earthquake. 1976, they lost. There's another 250,000. Sumatra, that was the tidal wave. 2004, Christmas 2004 killed 250,000 people. So the earthquakes and the tsunamis produced by them, as well as volcanic eruptions, a killer. How do earthquakes cause damage? Severe damage by motion will cause foundations to give way, walls to collapse, roofs to collapse, gas mains to break, water mains to break. The tidal wave can push ships up into dry land. Side-to-side motion, the S waves and the surface waves are the most damaging of all the waves because they're trying to break the buildings just with their side-to-side motion. Where do earthquakes most likely going to happen? This is the North American seismic likelihood map. And if you take a look, California has a much larger chance of having earthquakes, although this new Madrid area, middle part of the country. And you can swing over here to Virginia and see, and some more up there by New England and even Georgia down here. Here's the Virginia seismicity map. We're located right about there, and you can see that the earthquakes that happened in 2003 and also August 23rd, 2011, 5.8, which I'm hoping everybody who sees this felt this earthquake at some point. It was a very obvious earthquake, especially if you were sitting down. My wife was actually driving at the time and she did not feel it, but if you were sitting down, you probably did. What do earthquakes do? They cause a lot of damage. There's the 1964 Alaskan earthquake. We have foundations that actually give way as the soil becomes liquefied, as water moves up. And you can see that the buildings, some of them stood up pretty well, although they are still leaning and all the way to almost being horizontal. This is a tsunami in Indonesia in 2004. You can see it actually went through and exposed bedrock, took all the soil away. This is the before picture. Here's the after picture. So this is April 2004, and this is January 2nd, 2005, right after that Christmas tsunami. Here's another picture before, and if you take a look, it looks like a tropical paradise. Beautiful blue water. Well, not as blue as you'd like, maybe. You can see sediment coming down too, but you can see just normal waves. This is right before the tsunami got there, and as we're building up the crest of the wave, water gets pulled away from the beach, and you can see that actually got pulled quite a bit, and I'm sure lots of people ran in to, catch flopping fish and seashells and other things, while lots of other people were running away, and I'm sure sirens were going off saying, head to high heaven. And here's the result, where you can see water even all the way into here. So you had to do a lot of running to get away from that wave. I'll come back to this one because I think there's this slide here. I want to show you a little bit about a tsunami. Okay, we're going to hide the globe view because the tsunami is going to be actually, we'll leave it on there. Okay, so we're talking about open water. There's the displacement of ocean floor. The movement of the water got moved into, the movement of the land got moved into the water, sloshed the water back and forth, and you can see it moved out. It's going to move into this location where we're going to have an ocean ship, and you can watch the wave actually it looks like it's already passed, and it's gone. And then it doesn't really show up until it gets in shallower water when the beach moves up, because the wave actually stands up like waves do. And then it actually goes in, and then it sucks back out, exposing lots of beach, and then it rushes back in. And it does that, and eventually gravity will pull it back down to normal. Okay, the last thing I want to show you, if I can go back a slide, let's click this. This is a page of before and after put together by ABC News. I'm going to move my mouse over on this side because when it actually shows up what you're supposed to do, this is the airport, if I can do this, and you're supposed to just take your mouse, and as you move the mouse it exposes the after view, so you can take a look and see whatever the heck that was down here. Looks like it becomes more of a pond, and then we have some other things up there, gone, buildings down here, gone, and even the big building, actually it's not the building, that's the concrete. There's the building. Building looks like it survived, but almost everything else gone. And you can see lots of other things. So let's look at that farmland. Looks to me like we've got trees and farmland, and looks like we got rivers running down valleys in both the left side and the right center. And then here comes the water. Looks like the water didn't really hurt the higher land. There's even a dam right there. But look what happened to that farmland that was in the valley. And then again, didn't really get up into the highlands. But look what happened to all that low stuff. And red is showing you the absence of vegetation. So we've got vegetation and no vegetation. And I think that's about it for this one. 25 minutes. Thank you for stopping by. Appreciate it. Bye.